observer. Give you the common field. You need to be more accurate at this. Okay, giving, just giving system matrix A, B, C, D, and X, A plus 1 equal to A, X, K, plus B, U, K, and then we add call noise, that's the input noise K. Alright, and then YK plus YK equal to CSK plus DUK plus K nu K. And so that the assume that this input K is we call the input noise. Sometimes the people call it the noise, or state noise, and this is called output noise. If that and that random and what, and then now it is a optimal G such that state estimation A X K plus B U K plus G Y K minus Y K and Y K equal to C X K plus D U K. The state estimate and optimum G such that this is state estimator, the estimate state. That is this optimum G exists, but see there's the input noise and output noise, and however we have to know the A, B, C, D, and assume that you know the A, B, C, D. This is the common filter definitions. That's the common filter definitions. So that's the observer. That's the state estimate observer. That's what you call like this. It just give you more accurate the description of the common filter. All right. And so the common filter, the disadvantages of common filter optimum observer is that we have to know A, B, C, D. But in practice, A, B, C, D are not really known. They are not. You may have some error like that, and if you have some error, then this estimation won't be too good. Okay. That's just the exact description of common filter based on what you learned. Just the common filter, there's a book, you can talk about common filter for the whole semester. Okay, let us look at the AX model. The direct input-output relationship, input-output relationship, we have this. And that's the output output equal to the summation from I from 1 to k, then you have C A bar k minus I, B bar B I minus 1. Now if we expand it, then we have the U I minus 1, Y I minus 1 plus D U k. And you assume that the front part of this term we call beta. Then the real part of this term we call alpha. So we define alpha k minus I plus 1 minus alpha k minus I plus 1. And if we expand it, then we'll be able to write in terms of these formulations. That's beta k u0 plus beta k minus 1 u1 plus and so on plus beta 1 uk minus 1 plus beta 0 uk minus alpha k y0 and so on. I don't want to read the whole sentence. And that you can write in terms of this. We put all y on the output on the left hand side and input on the right hand side. Then on the left hand side involve y, on the right hand side involve u, and for that from I from 1 to k. Now, if we have observer like a g, and then we can choose the g such that this k won't be that long. So in the second here, final difference model is this. If we choose a p such that A bar P equal to all zero matrix. So here, now the P. Important sense is P. In the example, our P equal to 2, right? That's our example. We have a spring example and P equal to 2. Now here, we have a P here called A bar P equal to A plus GC P equal to a zero matrix n by n. So that equal to 0, 0, dot, 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 0. We have 0, 0, dot, 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 0, dot, 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 0, dot, dot, 0, 0. So this n column and n row, right? That's n by n zero matrix. Assume we can find a p such that that equals 0, right? Then we'll talk about the p later. In the example, we have p equal to 2. If we do that, then the matrix like here, then k from 0 to less than infinity, then k larger than p and less than infinity, then you can see that we have I from 1 to p, not from 1 to k anymore. So for example, p equal to 2, k equal to 1,000, then even that, then we have only I from 1 to 2, not from I from 1 to k. So k can be 1,000, 10,000, you have only I equal to 1 to p, for example. And I equals 0 to p, for example. So that means yk plus alpha 1 yk minus 1 plus alpha 2 yk minus 2 plus plus ap yk minus p. So we have only p terms here. So yk depend on the past output, p output. So y k minus 1, k minus 2, k minus p, then that's it. So that we have the current output depend on the past p output and also depend on the current u and past u terms. That's important. Now we don't have any state involved. There are no states. So you don't see any x. This is only output and input. There's no state, no x involved. So we don't need any state estimator for this. You look carefully from this, then you will be able to see that that no states in here. Go on. So, in the text description is the current output is the weighted sum of the current past P input and output. The weight means the alpha, beta, this is the weighting term. Alpha and beta, those are the weighting terms. We call weight. So, K, yk minus 1 is weighted by alpha 1. Yk minus 2 is weighted by alpha 2. And yk minus p is weighted by alpha p. And so on with beta, the same thing. Okay. Now the matrix, the A, B, C, and G are related. So there's a G is missing here, and I think you're wrong, probably okay, right? Okay. There's a G are related by this. The alpha 1 equal to C, A plus GC, and parenthesis I minus 1, B plus GD, and alpha 1 equal to C, parenthesis A plus GC, and I minus 1 G. And this is defined in the previous slide. And that's, if you look at the slide 26, you will see that I defined alpha beta there. Okay, and this is very easy to prove that. It's alpha beta. All right. Let us look at this example again. Very simple example, but very intuitive. So, the beta 0 equal to 1, that's equal to D. Beta 0 equal to D equal to 1, because we have acceleration measurement. Beta 1 equal to C, parenthesis E plus GD, parenthesis equal to minus 1. If you put your C in here, D in here, and G, we know G and D, then that's minus 1 minus cosine theta T. And beta 2 is C A bar B plus GD equal to cosine theta T. And this is simple, just I put A, B, C, D, and G in the previous example. I just plugged into those numbers. And beta 3, because A bar square equals 0, 0, 0, 0. So B beta 3 equals 0, beta 4 equals 0, and so on. Now alpha 1 equals CG equal to 2 cosine theta T. Alpha 2 equals C A bar B equal to minus 1. And alpha 3 equals C A bar square G equals 0. So when A bar, the power of A bar larger or equal to 2, then they are all 0, 0, 0, 0. So that's why we have R, start from R3 equals 0, 0. Okay.